Hi everyone, my name is Satyaam Raha. Welcome back. So in the last video, we have learned what are the steps behind the scene of training a neural network. Now let us zoom into how to find out the partial derivatives, right? So in the previous video, we got a column vector where we need to find the partial derivatives of the loss with respect to the weights, right? So now in this video, let me show you how to find out these partial derivatives. So I hope my screen is visible. Okay. So this is the column vector, right? We need to find out these four values for this particular diagram. This is a diagram for four neurons. Four feature data set, right? So how do we find out these partial derivatives? So I'll just write it here, dou L, dou W1. So this particular value, that is partial derivative of loss with respect to W1. See here, this loss is directly dependent on the function f, because this function f will actually give the output yi hat, which is the predicted value, and depending on this yi hat, the loss will be calculated, right? Loss is nothing but yi hat minus yi whole squared loss, right? This is L. So we got the L using the yi hat. So this L in return is dependent on f, and this f is partially, okay, let me write here the weights, W1, W2, W3 and W4. We are taking this example with a 4-featured data set. This f is dependent partially on W1, partially on W2, partially on W3 and on W4, right? So that is why the partial derivative is need to be founded, right? If this f were dependent on a single weight, then partial derivative will not matter, right? It would not have been necessary. But here, since this loss and the function is dependent on all these four weights, that is why we need to find out the partial derivatives with respect to each of these weights, right? So I'll use basic chain rule from class 11-12 mathematics. Okay, so this can be written as, we'll just break it down. Okay, see, dou L by dou W1 is nothing but dou L by dou f, that is derivative of L with respect to f multiplied by derivative of f with respect to W1. Sorry. This one, right? This is basic chain rule. This is simple chain rule from class 11-12 mathematics, differentiation chapter, partial derivative. Okay. Likewise, we can find out the others. W2 will be nothing but, you can write it on your own. Please make a note of it, because otherwise it will be very messy. You will not be able to understand anything. Okay, write it on your own. W3 is equal to dou f and dou f with respect to dou W3, and the last one is partial derivative with respect to W4 is nothing but by dou f multiplied by dou f by dou W4. Done. So these are the four elements of this particular column vector. So we can find it out using these formulas, right? Using these derivatives. Now the next question is very simple. That is, how do we find out these components? Okay, we broke this particular component into two components. Now we need to find out these two components, right? If we can find this out, we can do this similarly for all these four. Let us see how we can do it. Let us see how to find out this, right? So I'll write it like this. What is loss? Let us first define loss. Loss is nothing but the summation of I equal to 1 to n yi minus yi hat whole square. This is my squared loss for linear regression, right? And for this particular neural network. Now, what do I need to find out? I need to find out this. Let me take a different color. I need to find out dou L by dou W1 is dou L by dou F multiplied by dou F by dou W1. This is what I need to find out. So, how to find out this particular component, this first component? See, this derivative is with respect to f, right? F, the function f. So let me write this particular equation with respect to f first. Okay, so it will be like this: I equals to 1 to n yi minus f of w transpose xi, right, whole square. This is nothing but the same thing. Yi hat is nothing but f of w transpose xi, where in case of this perceptron, f was an identity matrix, identity function, right? Here also, since for linear regression, f is also an identity function. So now how you can find out the derivative? See, dou L by dou F. It is nothing but, you can write it like this. I'll just break it down in a very easy manner. Okay. Now L. What is L? L is nothing but summation of I equals to 1 to n yi minus f of w transpose xi, right, and whole square. This entire differentiation we need to find out. Now this summation will come out, right? Here you see this entire thing's differentiation with respect to f. So 2 will come in the front, right? 2 into entire thing. So yi, this is basic partial differentiation, right? Minus f of w transpose xi. Okay, and 2 minus 1 will be simply 1, right? So we got this, and now differentiation of this will be what? This is with respect to f, right? So yi is a constant basically, so it will be 0, and here f with respect to f will be 1. Yes, f with respect to this entire thing inside. Okay, so here f with f of w transpose x with respect to f is nothing but 1, right? So we'll only have the minus here, so minus to this. Okay, so we got this. Let me mark it as equation number 1. Now let me find out this one. So dou f by dou w1. What is this? Now see, we can write it as, I'll again break it down. What is f? What is f? F is basically f w transpose xi. This is nothing but f, right? Since this is w1, I'll write here xi1. Okay, so now what is the derivative of this? This w, right? Here we have a w, but you see this is an identity function, right? So we can write it like this. Basically derivative of w transpose xi1, since f is an identity function in this case. Okay, so here what we get, w transpose is nothing but a w vector, right? So w vector with respect to w is nothing but 1, and this xi1 is a constant, so it will come out. So xi1. So this is equation number 2. I hope this is clear. Basic differentiation. So now if we see what is, let me write it for ith point. Okay, so loss for a single point. We need to find the loss for all the points, right? So loss for a single point is nothing but dou Li by dou F multiplied by dou F by dou W1, which is in return nothing but minus 2 into yi minus, this is nothing but yi cap, right? We can see it from here. See, yes, this is nothing but yi cap, right? F of W transpose xi. That's what I am writing here. Minus 2 of yi hat, right? Multiplied by, what is this? Dou F by dou W1 is nothing but xi1. So we can write it like this, minus 2 xi1 multiplied by yi minus yi hat. Okay, so this is for a single point. And what is L? Then dou L by dou W1. For all the points, it is nothing but I is equal to 1 to n, right? Minus 2xi1, okay, yi minus yi hat. So this is the entire final result. Okay, I hope it is clear. See, this xi1, why this 1 is written? Because I am finding it for point number 1, weight 1. Okay, that is why I am taking the this particular edge xi1. So now you see this is for W1. So similarly you can find out for W2. Nothing will change, just here xi2 will be there. Everything will be same, just xi2. For W3 it will be similarly here 3. For 4 it will be 4. As simple as that. Okay, so if we can find this out, then what we got? We actually found out this entire column vector, right? If we can find this column vector, where can we use it? Actually, we can use it to update our weights, right? Remember from the last lecture, there you had a step called W. Let's say I'll write it like this: W1 new equals to W1 old minus eta times, what was the factor here? Dou L by dou W1, isn't it? This is the formula, right? Ablation of weight for each epoch, right? For updating weight 2, it was this W2 is the new W2. This is my old W2 minus eta times dou L by dou W2. And now we know how to find out this particular value. This was the question, right? How to find out this particular vector. So we can find this value now. So if we can find this value, obviously we can update the weights, right? And this will go on. This is nothing but what is happening in each epoch. These weights are getting updated. Okay, and at certain time, after certain epochs, what will happen? This W1, new W1 and the old W1 will be very similar. Okay, that means we reached convergence. That means the weights are not changing much. So we'll stop there. Okay, that is optimal W. Our main task was to find out the optimal W vector, right? So this is how we can find out the optimal W. So this is what actually happens behind the scene when we actually run the epochs in a neural network. Okay, so I hope I have covered everything here. I think nothing is left. If there is any doubts, any questions regarding this, you can ask in the comment section. Okay, and after having explained all these things, so the next thing is nothing but I'll show you how to what happens when we do it for an MLP, where we'll have multiple hidden layers, and obviously there will be more number of neurons. So it will be a bit complicated, the equations will be more, but yes, if you have understood this single neuron model, what is happening behind, then you will be able to relate to the MLP very easily, because that is nothing but an extension of this, right? It will be very similar to what I have done over here. This is the main concept. Okay, this is what happens, be it any number of layers, any big neural network. This is what happens behind the scene, nothing else. Okay, so I hope you actually understood the contents of this video. So in the next video, let's talk about the MLP model. Okay, thank you for watching. Bye.